Okay, this lesson is on parent functions. Parent functions really are the basic function of a certain type when you stripped it of all of its extra variables and extra pieces of information. Okay, it's the basic function of its types. When I talk about types, there's several that you're already familiar with. There's a linear function. Okay, the parent function of a linear function is simply y equals x. There's no m, there's no b, y equals x, and it looks like this. Straight through the origin, 45-degree angle cutting right through the quadrants. That is the parent function of the linear, making the straight line. You've also had experience with the quadratic. The parent function of the quadratic is simply y equals x squared and nothing else. It looks like this, the parabola. The parabola whose vertex is at 0, 0, and it's going up evenly. Okay? Now, I'm not sure what you had last year, but you should have had in algebra an introduction to the exponential function. Exponential function means that x is now the exponent. Y equals a some number to the x power. That makes an exponential function, and it looks like this, starting at 1 and going up, okay, in a strong curve. And the last one that we're going to deal with most of the time is called the square root function. You may or may not have seen that. The parent function of a square root is simply y equals the square root of x. What you need to notice about all of these is there are no coefficients, really. There are no constants, no intercepts identified. They are the basic function, okay? This is the square root function, which starts at 0, 0 and curves over to the right. So we're going to talk today about parent functions and how they can help you avoid extra work when you're trying to analyze complicated functions. Okay. Parent function help us predict the behavior of, as I said, of the more complicated functions. By behavior we mean, we'll describe the behavior of a function such as, well, it's steeper than the original function, or it's been transformed 3 spaces to the right or 4 spaces down. But we can talk about them relative to the basic parent function. How are they different from that? Okay? All functions start as their parent function, and we perform a transformation. Transformation, most commonly we'll see it translated down or up, to the right or to the left. Sometimes the transformation is a reflection or a dilation. When this slope gets larger, the line gets steeper. Okay? So these are the transformations that we're going to talk about when we describe how functions relate to their parent function. Let's look at an example. Okay, here's a function that looks fairly complicated, but what my eye should go to immediately is I see a y and an x and a squared. I know this is a quadratic function. It just has a whole lot of things going on. So the first thing I did is I drew in what the parent function would be. In blue, y equals x squared. And you know my graph is not perfect, but you can see what's happening. This should be at 0, 0 at the vertex, and then the 2 sides going up. But that's not what my equation looks like. There are more things going on. First of all, plus 6 means it's going up 6 points. So instead of going at 0, 0, I know it's going to start up 6 spaces. Okay? This x minus 2 inside here means whenever inside the parentheses it takes the opposite direction. So it's going to go 2 to the right. So now my vertex will be found at 2, 6. And we'll get into this in more detail a little bit later. Okay? That's my vertex. And then I know it's not the same steepness as the normal because I see this 4 here. Just like in y equals mx plus b, when I have a coefficient on the front or a leading coefficient, I know it affects how wide open my parabola is. In this case, it's 4 times steeper than it would be in a normal. So see how skinny that is going up. So I went up 6, to the right 2, and 4 times steeper. That's my description of this function compared to its original. Okay, so I want you now to pause the video for just a second and describe what you think y equals negative 2x squared plus 1 will look like compared to its parent function. Okay, let's do this now. So first thing I notice is plus 1. So I know it's going to go up 1. There's no number here with the x, so it's going to stay on the axis here. So it's going to move up 1, and see that negative 2? Negative means open down, and 2 means 2 times steeper. Okay? That's how this will relate. So if I were describing this, I would say this graph will be inverted, upside down, 2 times steeper, and its vertex will be up 1. It'll be here instead of at 0, 0. Okay, let's look at a linear function. Y equals 3x minus 5. I know it's linear because there's no exponents involved. So first thing I did was draw the parent function, which is y equals x. It would go through the origin and cut these right in half. Now what's different? Minus 5 means it's going to intersect at negative 5 instead of at 0, 0. That's my first difference. And then notice it must be 3 times steeper. So I draw it 3 times steeper. That's how I would describe it. So take just a second. You're going to pause the video and describe y equals negative 1/2 x plus 2 compared to its parent graph. Okay, so hopefully you caught that plus 2 means it's going to have an intercept that's up here at 2 instead of at 0, 0. That negative sign means instead of going up slope, I'm going to be going down. And then the 1/2 means instead of being evenly here, I'm going to be a little bit flatter. Half as flat, half as steep as this graph right here. So my graph will come like this. Oops. Okay? I hope you're seeing how these parents can describe. Now, this might be one you're a little bit less familiar with, the exponential function. Y equals 3 to the x minus 4. So I know what the parent function looks like because I wrote that down. And and if you didn't write that down, I hope when this finishes you'll rewind, go back to the beginning slide, and write down those examples of what those parent graphs look like so you have those in your notes as a reference. This is what the parent graph of an exponential function looks like. It starts at 1 because anytime a number raised to the 0 power, when x is 0, right here, 3 to the 0 would be 1. 10 to the 0 would be 1. 1/2 to the 0 would be 1. So all the exponentials without an intercept involved would be at 1. So this is the parent graph. But what I notice is I have minus 4. So the first thing I know is it's going to be down here. Okay? It drops. So just to double check, I know what my direction looks like and what my curve looks like, but I'm not really sure exactly where my points are. So your second step would be, let's plug in some numbers. When I plug in 0 for here, I get 3 to the 0 power, which is 1. 1 minus 4 is negative 3. So I came down and plotted 0, negative 3. When I have a 1, I have 3 to the first power, which is 3, minus 4 is negative 1. So I plot that, 1, negative 1. I have 2, which means 3 to the second power. 3 to the second power is 9. 9 minus 4 is 5, so I plot that point. And now this is where it takes off. Because now 3 to the third power is 27. 27 minus 4, and that's off my chart really. So I can see my key points and then whoosh, off goes my exponential. So graphing will always work. Graphing can give us an idea of how much of a bell I have in my different functions. And so it's a good idea to check your key points when you do that. Okay, now it's time for you to do some work. Use the graph of the parent function to sketch each of these 3 graphs. Please pause this and take a minute and see if you're successful. And I will get my marker and let's go. Well, I know the parent graph of this initial function is y equals x squared, and it looks like this. Okay? Except neater. But I see that this one's going to go up 5 spaces. So my vertex of my new graph would be here. Okay? And it's going to be twice as narrow. Okay? If I wanted to, I could plot a couple of points just to double check exactly how that curve is going to go. But this is, since it says sketch, sketch means you're using an approximation, so it's okay. The second one, I notice that it's linear because I don't have an exponent on my x. So first thing I'll do is draw the parent graph y equals x. But take a look, I have a minus 2. So I know I'm going to cut through here instead of there. And instead of this same slope of 1, I have a slope of 1/3. That means it's quite a bit flatter. Okay? So I'm going to get a graph that looks more like, whoops, not so messy. That looks more like that. Okay? And the last one, y equals the square root of x plus 1. The parent graph is the square root function, which goes like this. Okay? But it actually says plus 1 is the only change. So I'm going to take that same thing, and instead of going through 0, 0, it's going to go through 1. Okay? That is how we're going to use these parent graphs to help us understand the behavior of these graphs.